come on into the channel. Sorry, just doing one or two things before we get started. Is there anything like you can think of right up front that you want for me to cover, aside maybe from everything, but like a specific subject that you definitely wanted to? I mean, I'll cover everything on the exam, but if there's something like is probably going to be on the exam, but you don't understand it, so I can hit it before we get started. In other words, any requests? Yeah, we'll go over that. It's like the first thing we're going to talk about, actually. It's on the next slide. We're just going to go through those slides in more detail, the slides you have in front of you. And yeah, that's literally the first couple things. Okay, Tony, the big Tony, says he wants to talk about rotation movement on the spectroscopy. So we'll cover that, definitely. When we get to that chapter, that'll be at near the end of the session. Yeah, but just basically, since I'm going to wait another minute. And basically the answer is that, when stars move toward us, their spectrum are shifted toward the blue. When they move away from us, they're shifted toward the red. And then as they rotate, or if there's some reason you're looking at gases under pressure, or it's modified by magnetic field, will broaden the lines, right? This line broadening we learned can be from just normal temperature variations in the gas that you're looking at, or on being under pressure. It could also be due to molecular lines. If it's a molecule, due to vibration and rotation, in the case of a molecule. Okay, Ryan says he wants to know about calculating specific wavelengths, like the one question on the homework. I can go over that, although I'll tell you right now, the exam's not going to be that specific. It's not going to ask you to do that. But you should know, in general, what's going on with atoms absorbing light. And, it's kind of the definition of spectroscopy, right? Not just absorbing light, but how atoms interact with light. So Ryan, did you get that homework question in the end? Did you kind of figure it out? It's a little hard. It was definitely one of the harder questions in all of your homeworks. But there'll be no real massive calculations like that. You did not? Okay. Hey, if you can't get a homework question, you're going to shoot me an email. I'm happy to help you go through it. Okay, so maybe we'll go over that in class. Well, I could go over it later. Wow, so it was kind of a total dud. Now, the book kind of tells you how to do it, but it doesn't kind of go step by step or anything. It gives you the formulas to go through it. But maybe we'll talk about that when we get there, just for completeness. Or maybe, you know what, well, I'll mention it here, but I'll mention it in class too. But again, you won't be required to do calculations like that on the homework, or on the exam, I'm sorry. Okay, so let's get started. Maybe some folks will wander in. Okay, so exam 1, it's going to be on Thursday, 9:30. Bring a number 2 pencil or equivalent. You don't need to bring your own Scantron. I'll provide you with a Scantron. Bring a calculator. Again, the calculations will not be intense or at all, but just to maybe double check the simple calculations that you need to make, bring a calculator. You can't use your phone, so don't count on using your phone. Just bring a regular calculator if you got it. It doesn't have to be a scientific calculator either. It can literally just be like the old calculator from the 80s or something. Some basic calculator. It's not your phone. Okay, so it's going to cover chapters 1 through 5. It's going to be starting all the way from the beginning, all the way up into the end of the chapter on spectroscopy. So, I'm sorry, telescopes, not spectroscopy, telescopes. So it's going to be 40 multiple choice questions. Oh yes, thank you. We do get a equation sheet. I was just going to mention that just in this slide here. So 40 multiple choice questions, 2 essay questions. You choose 2 out of the 4 different ones to answer. So I kind of gave the strategy in class on Thursday where maybe you look at the essay and do the essay questions first and then go back and do the multiple choice questions. That may just be better time management because people can get lost in the many choices they have at the multiple choice questions. So that might be a good idea. But you can do whatever way you want. Maybe another strategy maybe is to go to the essay questions first and then make an outline and then go back. Later do the multiple choice questions and then kind of fill out your outline later. And it's always good on essay questions to do an outline. Like, you have a beginning thought, right? Okay, this is my thesis. It doesn't have to be a long answer, but lay out the points you want to hit. Okay, I know this, I know this, I know this, I know this. And this is how we're gonna connect these ideas, and then the conclusion. It has to be. It doesn't even have to be a sentence, really. Well, it has to be a sentence, but you don't need a very long conclusion. You don't need like a very large opening. So, basically, it's kind of make bullet points maybe, or you can just do the whole essay right there and then go back to the multiple choice question. I think that's what I would do, but it's totally up to you guys. No book, no notes. There'll be a formula sheet. So those formulas that we've been going over will be on the sheet to tell you that. So the problem is, I don't say what they are. I don't put them in context. They're literally just on the sheet. So hopefully that will help you in answering some of the couple questions where you have to do like some of the problems that we've been going over also in your homeworks too, right? And I'll talk about that in a little bit. And just the real basic like kind of relationship questions, like if something is 10 times farther away, how much less gravitational force will it experience? Things like that. And then, if the temperature of the star is twice that of another star, how much does that change its total energy compared to that other star? So it's things like that. Okay, so bring your UC card with your M number. And if you do have testing accommodations, you should have already made arrangements with testing accommodation services. But if for some reason like, oh, I forgot, let me know. Yes, so Lou asked a question, will the questions be more vocabulary and concept based than mathematical? Yes. There'll be a couple mathematical questions, but they'll be very general. And you can use the formula sheet to kind of help with your answers, help, kind of formulate your answers. But everything else will be kind of facts and things that like, just to give an example. What's a constellation? That kind of thing. So not a lot of math at all. Okay. So chapter 1 covered seasons, motion and phases of the moon, cosmic distance units, the celestial sphere, parallax, and constellations. What are they? And then chapter 2 is retrograde motion, geocentric models, There's the Copernican revolution, whom did what, so make sure you kind of know that. There's Galileo, right, and Copernicus, and all that stuff we'll cover in a minute. And Kepler's 3 laws of planetary motion, you should know those. Those are really important. And Newton's universal law of gravitation. And then chapter 3 is properties of a wave. We kind of went over this a lot in class. We got wavelength and frequency, EM spectrum, different categories of waves, which ones make it to the ground, etc. Which wavelengths does the atmosphere absorb? We'll go over that. Wien's law, which is kind of another sort of relationship to how to think about how the peak wavelength of a star's energy output changes with temperature. And then we talk about Stefan's law, which is the question I'm sure you guys were all talking about. That was another one. The Stefan's law, about calculating the energy. And then we saw what is spectroscopy, the structure of the hydrogen atom, stellar spectra, what do they look like? These are all topics that are going to be on the exam. So this is kind of like a more general, or actually more specific look at what we're going to be talking about with the slides in a minute. EM spectrum, higher energies and lower energies. Remember that? We'll go over that. Which part of the spectrum is high energy, which part of the spectrum is low energy. Think about the Hulk, maybe. Maybe something like stick in your brain, some kind of crazy reference that you would remember. Absorption, emission, and continuous spectra. Molecular lines, what causes line broadening. Kind of talked about that just a second ago. And what can we learn from spectroscopy? What is it good for? And then chapter 5, telescopes. Difference between reflectors or reflection telescopes or refractors and refraction. What those two things mean. The different general telescope types. I kind of just mentioned them just now. Which do we use today mostly and why? Again, if there's glitches that are really bad, let me know, because I really can't see the glitches on my end. I just noticed. I do get like a little notice when the bandwidth starts going south, but I don't know how that looks on your end. Anyway, what limits a telescope's resolution? So you should kind of maybe memorize or kind of a good idea for the angular resolution, the formula for that we went over in class a couple times. And we'll go over that in a minute. James Webb Space Telescope basics. What's cool about the James Webb Space Telescope? The ALMA array, same thing. What's kind of unique about it? Or what's the most powerful thing about it, perhaps? And then radio astronomy. Why do we use big dishes for radio astronomy? So these are all really good hints for the exam. Okay, stars and galaxies. Let me move this out of the way. Move the window. Okay, stars and galaxies. Overview and our place in space. This is chapter 1. So I'm going to just cover, again, these are the slides you guys have, the exam 1 review slides. So these just kind of cover those topics that we talked about in the slides. You may have been looking at them in class. Okay, so the universe is really big, right? It's huge. It's so big that we need a new ruler. I mean, we can talk about kilometers and miles and how big the universe is, but it's just a lot of zeros and everything would be in exponential notation. So we just have to make a bigger ruler. We invented this thing called a light year. And there's nothing really magical about it. It's not a special unit per se, but it's just a big one. And we just base it on how far light travels in a year. So again, light year is not a unit of time. It is not a special new diet supplement. It is a unit of measurement. It's like or length, I should say. It's like a mile. It's like a meter. It's like an inch. And it's about 10 trillion kilometers. The distance the light travels in 1 year. It's really long. I mean, light is super fast. In a year, it's going to travel a long way. Okay, so what are constellations? Constellations are groups of stars that we have with our imaginations because humans are really good, essentially too good, because it messes us up a lot of times. We start seeing religious figures in toast and things like that. We're really good at identifying patterns. So we looked at the sky and went, huh, that looks like a guy up there. Looks like he may hold a sword. One of my gods is Orion. One of the stories in my mythology is Orion. So surely that must be him up there. And that kind of goes for all these other mythological figures throughout the sky and throughout history. So in all cultures seem to do this. Native Americans have their own constellations. The Chinese have their own constellations, usually based on animals and gods and things that kind of were in their everyday lives and essentially the stories they wanted to tell. These constellations are not bound together. They're not like physically close to each other in the sky, the stars that make up the constellation. It's just our line of sight effect, right? I'm looking at my window here and I'm looking at a woodpecker actually right now looking at me in my tree outside my window, and I know that the trees behind it are at a different distance, right? It's easy to tell. Stars, it's not hard. It's not that easy to tell. It's harder to tell what's in the foreground and what's in the background. So we can do that by measuring redshift, for instance, or we can do that by measuring really parallax. That really tells us what's in front and what's in back. So that's a good thing to know. Okay, so the celestial sphere is this imaginary sphere, right, that all the constellations, which look to us like two dimensions, sit on. Now, of course, this is not really the case in reality. It's just what it looks like to us, and it's very useful, though, in trying to say what's in the sky and where it is. Because from our point of view, it really does seem to form an imaginary sphere around us, right? Because it rotates around. It goes from horizon to horizon all the way around us. So it's a hemisphere as far as like we're concerned, as far as when we see it. But it's a whole sphere, really, when we talk about the whole Earth. So the stars seem to be on the inner surface of this imaginary sphere, but they aren't, of course. But we can use two-dimensional spherical coordinates, if you've studied spherical coordinates before, similar to latitude and longitude, to locate where things are on the celestial sphere. So the celestial sphere rotates around, right? The Earth doesn't rotate. I don't see the Earth rotating outside my window right now, and neither do you. But the sky is rotating, right? The sun is moving. And that's not the sun really moving, although the sun moves a little bit every day. But it's the Earth moving, right? It's the Earth spinning. That makes the celestial sphere look like it's rotating. So how long or how fast does it rotate? It makes a full rotation in our sky every 24 hours. That makes sense, right? The sun rises every 24 hours. So it means it's on one part of the celestial sphere in the east, and then comes up because it sits below the horizon, then it comes underneath us, and then it comes back up again after 24 hours to do the same thing again. So how much in 1 hour? How much does the celestial sphere go in 1 hour? I think this is probably in your homework, but it was a long time ago. So this is something you will definitely need to know for the exam. It's 15 degrees, right? So if you just take 360 degrees, divide that by 24 hours, what do we get? 15 degrees, right? For 1 hour. So one thing to maybe remember your calculator for. If you can't remember that kind of quick fact, you remember that like a day is 24 hours, right? And we have to go through, the celestial sphere has to go 360 degrees to get around to the start again. And so that you can just figure it out with some very simple calculation. Okay, what are some of these things? Not all of these things are going to be on the exam. I did not emphasize them for that reason. But there are a couple things that you should definitely keep in mind. So the ecliptic, you may remember, is the plane of Earth's path around the sun. So here's the sun. Here's the Earth. It's going around like this, almost in a perfect circle, almost. And as it does that, it's going around like in a plane, right? It's like a circle. It's not like going up and down or left and right or changing from orbit to orbit. It's going on in a nice flat circle. But again, from the Earth, what does that look like? It looks like the sun is moving through our sky, We're not talking about the day-to-day motion. I'm talking about like the motion, like if you were to measure the sun at noon every day or 8 o'clock every day and kept track of where it was. It would look like it was slowly moving against the stars and then, make a full circuit around the sky in a year. So what is that path through the sky called? That's called the ecliptic. And it's tilted 23.5 degrees to the celestial equator. Now what's the celestial equator? The celestial equator is just the Earth's equator projected out into space onto the imaginary celestial sphere. So what does that look like in the sky? It looks like a big line going from east to west, kind of tilted up depending on what latitude you're at. So at the North Pole, for instance, Polaris, the North Star, is going to be right above you, right at the top of the sky, and it's going to stay there. And as the Earth turns from the North Pole, everything kind of moves in a circle. But if you start to move down, and I walk toward the equator, all of a sudden, the North Star starts to become behind you, and the celestial equator starts to tilt up, right? So you're at the North Pole, it's like this. The equator here, the celestial equator, and the real equator that you're looking at are all in the same spot. And then the North Star is like here. But as you go down the equator, boy, it looks silly. I just saw that in my picture. So if you go toward the equator, everything goes like this, right? If you're going, then finally you get to Cincinnati, where the celestial equator is at a certain distance, the North Star is at a certain distance, and there you are. That's what things look like in the sky. But then there's kind of these points where the celestial equator meets the ecliptic. And these points are kind of important because they mark sort of how high the sun gets in our sky. So as it turns out, when the celestial equator, the point in the sky where the celestial equator is farthest below, has the greatest distance below the ecliptic. In other words, so here's the celestial equator, and the ecliptic is here. So that means the sun is really high in the sky. So this is summer solstice. But as the year goes along, the highest point in the sky that the sun would ever get gets lower, right? The sun doesn't get that high in the wintertime at its highest. It gets low. And that's the reason we have seasons. So at some point it's going to hit the celestial equator, though, and those are the equinoxes. So the vernal and the autumnal equinoxes, spring and the autumnal equinox. And then finally, in the wintertime, it gets to its lowest point from the celestial equator, and that is the winter solstice. So highest point, summer solstice, highest point of the ecliptic above the celestial equator, summer solstice, lowest point, winter solstice. When it hits the equator, those are the equinoxes. So equinox, equal, right? Those two distances are equal. Hopefully that makes some sense. It's a little hard to describe. This is like literally one of the hardest parts of the course, just imagining all this. It's a little easier if you're in a planetarium, but even then it's still kind of hard. So a combination of day length and sunlight angle gives all the seasons. So the Earth is tilted 23.5 degrees, right? So it's that angle that gives us the season. It's not because we're closer to the sun in the summertime. We're not. We're closer to the sun in the wintertime. Believe it or not. That sounds totally wacky, but it's true. So the tilt of the Earth gives us the seasons. Why? How does that work? Well, this little diagram right here, where, let me zoom in a little bit, right? If we're tilted toward the sun, the Earth is kind of tilted, and we're in the northern hemisphere, we're tilted toward the sun during the summer, then the sunlight hits directly and the energy per square inch is greater, right? It's taking the same energy over like a kind of a smaller ground area. So the energy is more direct, and that causes more heating of the Earth. Now, in the wintertime, when we're faced away from the sun, we're sort of tilted away from the sun like this, again, as we're spinning here, the sunlight is much less direct, right? We're spreading the same amount of energy from here over a larger area. So less energy per square inch, that causes less heating of the Earth, and so we have cooler weather. So the atmosphere doesn't get warmed up as much. Okay, does that make some sense? I'm going to take that as a yes, or maybe, or perhaps to come. Okay, let's talk about angular measure a little bit. We talked about this a bunch of times in class. So we have to measure things in the sky, right? You can measure things with a ruler. Hey, that sun looks like it's an inch wide. Well, how are you measuring that inch? Is it like from here? Is it here? Because it's here, it's not an inch, right? It's smaller than that. But if you measure here, it's like, it could be like this, depending on where you put your ruler. So it doesn't work. We have to actually use some universal measurement, and that is angles. It's always the same angle in the sky, no matter where you're measuring it really from. There's an angle that emanates from you to the celestial sphere, and that is a certain angle. The whole celestial sphere is 360 degrees, right? So how much is the sun taking up of that? Believe it or not, it's about a half a degree. And same for the moon, it's about a half a degree. So those are degrees. Then we break down the degrees into what's called arc minutes. And there are 60 arc minutes in every degree. So that's just the way it is. It is kind of based on time a little bit, but don't worry too much about that. Just kind of know that it's arc minutes. I mean, it sounds like time, right? I know it's confusing. Time and space and astronomy are very linked, and not just in like the Einstein way. There's, we measure things, and how long it takes, like for the sun to go around, right? And that's a year, and so everything's like in years. So it kind of makes sense that we start to measure things in the sky. Time sort of works its way into measurements of size. So anyway, there are 60 arc minutes in a degree. Again, it's arc minute is not a unit of time, it's a unit of distance. It's an angular measure. It's literally an angle. It's like a degree, it's just much smaller. I mean, we can measure these things in 0.0002 degrees. That's really hard to describe. Again, we get into exponential notation, and for other historical reasons, we don't do it that way. Some astronomy does do it that way. So anyway, 60 arc minutes in a degree, or 60 arc seconds in each arc minute. So you can kind of see how tiny an arc second is compared to 260 degrees. It is tiny. All right. The angular size of an object in general depends on its actual size and its distance from viewer. Here on the Earth, we're all, of course, essentially the same distance away from, from the things in the sky. I measure the same angular distance to the sun as you do, and you're in Cincinnati. So, in that sense, it's the same when viewing from Earth. But when we start to measure other things, then it can start to matter. Just talking about angular size and measures in general. So just kind of know that. Okay, so the moon. The moon takes about just under a month, 29 and a half days to go through the whole cycle of phases. It's called the synodic month. Things that are synodic has to do with the moon, so kind of think of it that way. Again, how long does it take for the moon to go around to orbit the Earth? It takes a month. That's not a coincidence. Month is short for moons, and we divide our calendar into how many times the moon goes around the Earth in a year. So that's not exactly 12, but it's close, right? We kind of fudged the calendar a little bit with some shorter months and longer months to kind of make up the difference. But that's what a month is, moons. Hopefully that helps. So we see the same face of the moon because the moon is spinning the same rate as it orbits the Earth, right? We kind of went over this last a couple times. So as you go around, as the moon goes around the Earth, it is spinning. to always show the same side facing us, right? But that doesn't mean that the same side that faces us is always going to be lit by the sun in the same way. Because the moon is going around the sun, different parts of it are going to be illuminated. But that illuminated part is not always our side. So that's why we get phases. So don't get too into the woods about which phase is what and what time of the day it appears. For this class, we're not going to get into that much detail, but do certainly know why we have phases, why we see the same side of the moon, and how long it takes for the moon to go around the Earth. And where do we get our eclipses? Right? When the moon is here, we have new moons. We can't see the moon because it's in the daytime sky and it's near the sun. I mean, it's there. We just can't see it with our eyes. It's too bright. The sun is too bright. And there's no lit side of the moon for us to see that with. The lit side of the moon is on the other side of the moon. So that's when we have a solar eclipse. Sometimes this moon can go in front of the sun and block the sun, right? It can only happen here. It can only block the sun here if the sun's over here. And then on the opposite side, over here, on the night side of the moon, the Earth is casting a shadow, right? And sometimes if things line up just right, and this happens in cycles, then the full moon will cross into the Earth's shadow, just like it did the other day. And that's when we get a lunar eclipse, when the moon passes through the Earth's shadow. And lunar eclipse, solar eclipse. What's being eclipsed? That's how you know. What's being eclipsed? What does eclipse mean? It means to block, right? What's being blocked here? The sun. What's being blocked here? The moon. So hopefully that helps. Okay, any questions so far on all this fun stuff? Okay, let's talk about parallax. Oh, we went over this class so many times, but here's a refresher. So basically, as soon as you hear the word parallax, all right, I'm going to pretend I'm psychic. What do you guys do? As soon as you hear the word parallax, what did I teach you guys to do? Right, you put your finger right up to your face, right? And you look kind of silly. That is parallax. Literally, you're just telling yourself what parallax is. It's how things change depending on what eye you're looking at, right on your face. Your finger is moving against the background, right? You can blink your eyes back and forth, and your finger literally moves back and forth against, I guess, my face if you're looking at the screen or, whatever it is you're looking at. So the same thing with the Earth. We can use the Earth and just look at the stars at different baselines, right? Kind of like you're moving from one eye to the other. You're literally moving in space to see what moves. And if it's moving like this, you can calculate exactly what that angle is, how much it's moving, and then you can translate into a distance, how far away it is. So parallax also, so here's the star version of that your finger is representing, right? So your two eyes would be equivalent to these two Earth positions here. So you measure the nearby star here, and then all you do is sit on the Earth and wait. The Earth is like a spaceship. It takes us around to the other side of the sun 6 months later, and then you look at the same star again, and then you measure its position, and whoa, it's changed in relation to the background stars over here. So we can measure that angle, and that angle can give us the distance. And how does it give us a distance? They're inversely related. So the bigger the distance is away, the smaller parallax you're going to get. How can you figure that out? Again, through your fingers. Parallax. Put your fingers up to your face. Look, put them right at your nose. See how much distance there is between your fingers? Now move your finger farther away. The distance, and again, look at the background. Don't look at your finger. Look at the background. So it's kind of like one of those magic eye puzzles, if you've ever seen those. And then look at your two fingers here. Much smaller distance here, right? Compared to here. So the farther away an object is, the smaller its parallax angle is going to be. Smaller angle, bigger angle. Does that make sense? Maybe I'll leave it there. Okay. So, was that a repeat slide? Oh, I think I put up an additional point. Oh, yeah, I did. So I meant to delete that slide. It's probably a kind of a mistake. So the combination of day length and sunlight angle gives seasons, right? So the angle of the Earth, is one dimension, gives the seasons, as I mentioned, but also, the amount of sunlight during the day also gives the seasons. The days are shorter, kind of necessarily because of this geometry, and so we used to have less time to heat the Earth to then heat the atmosphere, or heat the atmosphere directly, and so we get cooler weather. Okay, chapter 2. Any questions about chapter 1? Okay. Chapter 2. Well, you're on delay, so I apologize for that. I'm used to being in class, so there's like a 5, 6, 7 second delay by the time I speak and by the time you hear it. So apologies for that. So don't feel bad about asking questions in the chat. Okay, so basic layout of the solar system. We have 2 types of planets, inferior and superior planets. Don't worry about that too much. Inferior planets just means it's closer, orbits are closer to the sun, to the Earth. In other words, there's only 2 inferior planets, Mercury and Venus. And then all the other planets orbit outside of the Earth, and they are called superior planets. But superior planets undergo what's called retrograde motion. We learned about this, right? It's where, from our point of view, it looks like from night to night, again, the planets wander along the sky, right? Kind of just cruise along the sky from night to night. I'm talking about during the day when stars are rotating. But if you were looking at measuring the planet from night to night, it would actually move in the sky from where you would see it from the previous night. And then retrograde motion is that the planet does something weird. Instead of moving one direction, it stops. It reverses direction, and then give it a couple more nights, and it starts going the other direction as well. Okay, so we got a question. Lou asks, so are inferior and superior planets only exist in our solar system because they are based off of the location of Earth? And that's correct. So we haven't studied other planetary systems yet. But yeah, this is purely our solar system thing. Again, don't worry about inferior or superior too much. We're not studying the solar system. We kind of jumped over some of these things a little bit for the sake of trying to get, maybe unsuccessfully, to material a little faster. But anyway, just kind of know what retrograde motion is for sure. And here's a picture of retrograde motion. You can literally see on the different days how things are moving in loops as the days go along. This is Mars. Mars is maybe the most famous example, and it certainly has the largest retrograde loop out of all of the planets. Now, why is that? That's just because Mars is close. Closer than Jupiter, right? That's the next superior planet out. Earth, Mars, Jupiter. So Jupiter is really far out there, or much farther out there, 5 AUs. Okay. And then here's how the geometry works. So what's actually happening in reality? This is what Copernicus figured out, right? We had our geocentric model of the universe, and it said that the planets had moved around this Earth, and the sun moved around the Earth, and we got retrograde motion because, well, as the planets moved around the Earth, this is Ptolemy's model of geocentric, where the Earth is at the center. This is, of course, not correct, but this is what we thought for many centuries. So as the planets go around, they're making loops like this around the Earth. They're literally making like a spirograph pattern. So when we see retrograde motion, Ptolemy said, oh, that's just the planet going around in a circle away from Earth before it comes around again in another circle. The crazy thing about that is that it worked from a observational point of view. You could actually explain it that way. It would actually make these things. Now, of course, that wasn't the case. Copernicus, kind of revived an old Greek idea that had fallen out of favor, that the sun was at the center of our solar system, not the Earth. And so he explained retrograde motion like this, right? Here you have the Earth, here you have Mars, and as Earth, us, looked at Mars, it would trace out a pattern like this as we overtook Mars in its orbit, because we're orbiting faster than Mars, right? Copernicus figured that out, even before there was Kepler, to really give it a mathematical foundation and really solidify the relationship there. But yeah, so we're moving faster than Mars because we're inside the orbit. And as we pass Mars, Mars is still kind of slow, slowly is trying to get around this part of the circle. And as we pass it, it makes this kind of retrograde loop as seen from Earth. Okay, so here's a good example of that epicycle, the Ptolemaic version of what happens. The planet goes around in a circle around some empty point in space, and as it goes around the Earth. Now, this is Ptolemy. This is not correct. This is not what Copernicus thought. Right? Copernicus came and wanted to throw this idea in the toilet. Now, he was a very religious man. He believed, in honoring things that were kind of set in stone. Certainly, the church at the time believed this. So it was very dangerous to go against the church. But Copernicus, he really struggled with this. And it's why he delayed publishing this book for so long. Oh, is that right? Sorry about that. You can't see my cursor. Sorry about that. You can't see my cursor. I remember that from last time too. Is there a way to do that? I'll just use my hands. I can't really go over here. Can I do that though? Let me try. Hey, I can just move my hand over here. Look, I'm gonna grab a planet. So, it's moving around. It's hard to do. Getting the motion right. It's going around. What direction is it? Maybe that's harder. It's going this direction, right? It's going around essentially counterclockwise. Anyway, you get the idea of what's happening. Oh, there's a show cursor option. Let me see if I can see something like that. There's really not. Okay. I'd have to totally redo things. Anyway, sorry for the glitch. I noticed that there was a low bandwidth thing going on there. Okay, so let's move on to the next slide. I think you guys have a good idea about that. And this is how crazy it looks like when you put all the planets and the sun together and what's actually happening according to Ptolemy, according to the geocentric theory of the solar system. Okay, so here's the Copernican revolution. Came along to kind of hopefully upend all that and give us a much more better idea for how things really worked. This is where sort of dogma stopped and the scientific revolution began. The Enlightenment began. It's kind of at the same time as the Renaissance. So it's a pretty amazing time. As I mentioned, Copernicus, he published De Revolutionibus Orbium Celestium. Don't worry about memorizing that, but just kind of know that he came up with the idea that we talked about. So the prose, much simpler than the prose of the Copernican system, with the sun at the center. Better idea for how things really worked. This is where, sorry about that, I got a little feedback. I'm not sure why it suddenly started to work. Let me know if you can't hear me or something for some reason. Anyway, the prose of the Copernican Copernican model, I should say, much simpler than the geocentric circles within circles, right? It's a very much simpler model compared to the Ptolemaic version of the geocentric part. So that's a good thing. Bad thing is that it actually didn't make any better predictions in the sky than the other model did. Can you believe that? If you put planets going around the sun, it didn't make any better predictions as this model would in our sky. So that's why I wasn't kind of very sure about it either. So why is that? We know that's correct, right? We know that that's the way it is. Why does it make better predictions? And that's because the orbits aren't circles. The orbits of the planets are ellipses, and that wouldn't be discovered until, of course, Kepler came along. Okay, so this is another guy from the Copernican Revolution, Galileo Galilei. He did very important experiments and essentially invented the astronomical telescope. The astronomical telescope. He was the first real observational astronomer to use a telescope. He took a look at the moons going around Jupiter, for instance. That was pretty cool. He looked at sunspots. Started to go blind because of that. He saw that Venus wasn't just a dot in the sky. He saw that Venus had phases. And, you know, you shouldn't see those phases that he was seeing if Venus was going around the Earth and the sun was also going around the Earth. So you should not see the phases that he saw. And this is kind of a diagram of that. So this is a really critical piece of evidence for the Copernican theory of how the solar system worked. Because Venus, as a sphere, should have phases that look like this, right? Just like very thin crescent phases. And here's the sun out here. And it has its own epicycle, I believe. But here's the reality, right? And this is what we saw. We saw like very large phases, like gibbous phases, like half Venus phases and things like that. You would never see those in this geometry. So Galileo, famous for Venus phases, for observations. He did experiments with gravity. He kind of laid all the groundwork, really, for Newton. And also helping along the way were these two folks, Tycho Brahe, who made very precise measurements of the position of Mars in the sky with his observatory. He's kind of a sextant-like object to just measure the very accurate angular distances between the stars and also between stars and the planet Mars and other planets to really track them through the sky. It's hard to do. It sounds kind of easy, but it's hard. Okay, and then, Tycho Brahe hired Kepler to help him with things. He was kind of jealous of Kepler, I think. Withheld his best data from Kepler and then he had a big feud. Then Tycho Brahe died. Don't worry about all those details, but it's kind of leading up to the point where Kepler was able to use Tycho Brahe's measurements of Mars to nail down the geometry of the solar system and how things moved. So he came up with his 3 laws of planetary motion. You will definitely need to know these. Kepler's first law, the basic summary of that, of the planets do not go around the sun in circles, they go around in ellipses. And these ellipses are kind of like, this is a kind of conical section, right? And then you have like a focus here at the sun, and then you have nothing over here in this focus here. So like two foci, and an ellipse. Sun is at one area, one focus, nothing in the other focus. The semi-major axis can be mathematically proved to be the average distance between this planet and the sun. Now, this distance actually varies a lot, right? Or it can vary a lot. But if you measure the semi-major axis, the distance from the center of the ellipse, not the focus, but the center to the edge, that's the average distance. So yeah, again, I'm using my cursor, sorry. But I think you get the idea. You can look at that diagram. So perihelion and aphelion, closest point and farthest point. That's Kepler's first law. The big thing about Kepler's first law, planetary orbits are ellipses. Second law, a planet moves faster in its part of its orbit nearer the sun and slower when it's farther from the sun, sweeping out equal areas in equal times. So the big thing here is that, Kepler's law is talking about going faster and slower. not for planets, different planets. It's talking about going faster and slower within the orbit, right? Within the same orbit. So as a planet in its orbit gets closer to the sun, it's moving faster. As it gets farther out, it's moving slower, right? It gets faster and then slower as its year goes along every year. We're not talking about how fast it goes, for different size planetary orbits. That's the third law. Again, first law, ellipses. Second law, how fast the planet goes as it gets closer to the sun. Third law is about different planets, so also Kepler's second law, sweeping out equal areas in equal time. The third law is about how far a planet is away and how long its year is, how long it takes to go around once. Okay, so the key thing here is Kepler's third law is a cubed. A is the semi-major axis, is equal to p squared. P is the period, right? It's the time it takes to go around the sun. So if we measure all these in astronomical units as the distances and years as time, Earth years, then this is true. A cubed equals p squared. Otherwise, it's proportional. Don't worry about that being confusing. Just look at the equal part. That's the only thing you really have to know. Okay, then here's a nice little chart describing that mathematical relationship. This is amazing. He's able to do this. So in other words, just by measuring how long a planet's year is, in Earth years, like Saturn, for instance, takes 30 years to go around once in our sky, you can figure out how far away it is. That's pretty amazing. If you know how far away it is, and you can measure its angular distance, the angular size in our sky, I should say, then you can figure out how big Saturn is. So all kinds of things fell out of this discovery. And especially it was super helpful when Newton came along. Everything's still good? You guys still with me here? See and hear everything okay? Alrighty, so then we had Newton to wrap it all up. Newton came along. He kind of combined all the work from the previous people in the Copernican revolution, and then he came up with his laws of motion. Good. Thank you, Tony. And then, so he wrote a very famous scientific scientific treatise called the Principia, which is maybe the most famous scientific work of all time. Certainly up there with the Origin of Species. Pretty much you have the Origins of Species, you have Principia. You could certainly put De Revolutionibus there. I'm probably missing a biology one. I'm not a biologist, so I can really kind of put that in a context. But and what are we missing? And probably, the theory of relativity, per se, Einstein's papers about that. Anyway, so this is a really big deal. He invented modern physics. Didn't exist before Newton. He invented calculus, or co-invented calculus. So that didn't exist then either. To help explain the motions, and he of course married the motions of the heavens to the motions we see every day here on Earth, and that was another really big deal. So here is Newton's law of gravitation. So kind of know how these work, right? Kind of know how this works. The force of gravity that the two objects experience is equal to the product of their masses in the numerator, or you can just think of the masses in the numerator, and the radius squared in the denominator. So if we were comparing two objects, and the only thing that changed between them was the distance, say something was twice as far away. So say at one point, both objects are going around the sun. So we're comparing one object, and it's, we'll say that's essentially one. And we compare that to another object that's 2 times the distance away as the other object from the sun. How is the force of gravity changing for that other object compared to the first one? Well, it's twice as far away, right? So we have 2 down here in the distance. This is r. So this is the distance between them. So we have 2 times that distance now. And so it's going to be 1/4. It's going to experience 1/4 the gravity, gravitational force from the sun as the other object. So like, for instance, trying to find a good example. Let's say we're talking about Jupiter. Jupiter is 5 AUs away from the Earth. So, which means it's 5 times the distance away from the sun, right, as the Earth. So how much does the force of gravity due to the sun differ at Jupiter compared to the Earth? So gravity at Jupiter compared to gravity on the Earth. Gravity due to the sun on Earth. So it's 5 times farther away. Well, that's easy. It's 1/5 squared, right? 5 times the distance. So that's 1/25. You go away just 5 times, your force of gravity diminishes tremendously. 1/25 as much force of gravity from the sun as on Earth. Does that make sense? Okay, chapter 3, radiation. Oh, sorry. Okay, well, we learned about radiation. Is essentially just an oscillating quantity, electromagnetic fields. So we have electric field, we have magnetic fields, and basically things are just changing like this. Like electric fields are going on like this. Brighter and dimmer, bigger and smaller, as far as like how much of an electric field we can get from space, from anything. Same thing with magnetic energy. And if it's oscillating like this, we can think of that as a wave. So there are certain characteristics of periodic motion, just waves. And waves come in all kinds of shapes and sizes of anything that varies on a regular basis. You heard the different aspects of a wave. We have wavelength, right? The distance between waves. I always talk about, sitting or standing, I should say, like maybe waist deep at a beach with the ocean coming at you, right? The waves are coming at you. So the distance between wave crests, you can literally, if you had a tape measure or a ruler, you can measure that distance between the waves. That's called the wavelength. How high the wave is in the water, is that like a low wave, is that a big wave, tsunami, that's the amplitude. And this whole thing is moving, right? That's a very important thing to keep in mind. So it's moving this way. So if you're standing here, I'm moving my cursor again. So if you're standing all the way on the right-hand side, say you're standing right where this arrow is, but up where that dashed line is, you would experience like a low wave. And then you would experience a high wave and then a low wave, right? That would all kind of hit you as you just sat there. The whole wave train, it's literally called a wave train, is coming at you and you're experiencing high, low, high, low, high, low from your point of view. This is a crest, this is a trough, by the way. Okay, so other things are happening too. You're getting hit by a certain number of crests every second. Like, right, if you literally had a stopwatch and you counted how many crests hit you on the beach, 3. That's 3 hertz. That's what the frequency means. You can also measure how long it takes for just one crest to hit you. Like how long does it take for one crest to hit you to the next? Start your stopwatch. As soon as one crest passes you, and stop it when the next crest hits you. That's the period of the wave. That's how long it takes between crests. And they're related, right? So the period equals 1 over the frequency. And what that just means is that when we talk about a frequency, how many wave crests are hitting you per second, what your period is, what the time is in seconds for each wave crest is just like the inverse of that. So just to give you an idea, So say I'm standing on the beach, and I'm waist deep in water. The waves are hitting me, and I'm measuring how many wave crests are hitting me. And I have a stopwatch. Ready? Click. 1, 2, 3, 4. Whoop. That's not to scale, but if, say in 1 second I've actually measured 5 crests hitting me. I could literally feel it. So that's 5 hertz. So you could just literally take the inverse of that. Frequency is 5, 1/5, 1 over seconds. Hertz is 1 over second, so you get essentially 1/5 of a second for a period, right? So 5 crests hit me per second. How many crests are hitting me? What is the period between crests? Well, it's 1/5 of a second. Does that make sense? They're related like that, right? Period, you can get the frequency. Frequency, you can get the period. Okay, we talked about wavelength. The speed is what the crests move. Like literally, this wave train is moving. It has a velocity. And don't worry about this too much. Velocity is the wavelength over the period, though. It's the distance it travels. It's traveling a wavelength as this whole thing is moving in 1 unit. It's moving a wavelength over the time it takes between wavelengths. So it's just distance over time. Wavelength over period. Okay, so you know and love this hopefully by now, the electromagnetic spectrum. There are a bunch of things you need to know here, but it's not too complicated. I'm not going to question you on like how big your fingernail is, for instance. But let's talk about frequencies and wavelengths and energies and all this too, right? So we talked about, first of all, this spectrum here, right? We have long wavelengths here. There's a really big distances between crests here. Very small distances between crests here. So much larger wavelengths here, much shorter wavelengths here, right? So what about frequency? Well, this means frequency. We'll kind of look at it, right? Frequency is going to be small here, right? Because you're not getting hit by very many of these waves. You're not frequently getting hit with a wavelength this size if it can be continuous and stay the same wavelength. Over here, if you're looking at one particular wavelength, it's pretty high, right? The frequency, you would get hit with a lot of these per second if they were all traveling the same speed, which of course they are. All of these wavelengths, no matter what wavelengths you're talking about, are traveling the same speed. Oh, sorry, I missed your question, Lou. So Lou's question is, so will the 1 change if the time period is increased? So do you mean... no. So it's always just the inverse, right? If you think about how period and frequency are related, it's just literally the inverse of each other. So the 1 doesn't change. As the time period increases, if this gets bigger, right, what happens to the frequency? So if this is big, what happens to the frequency? This has to be small, right, to make for this fraction to end up being a big number, right? So that's just what happens if the period is increased. So they can literally do it on paper too, like again, period. Okay. So yeah, like if you're think of it in frequency, right? If you're getting hit by 10 wave crests in a second, right? It's getting battered, 10 wave crests per second. Well, how much time does it take for 1 wave crest to hit you? Well, 1/10 of a second, right? For one when they hit you. Hopefully that makes some sense. Yeah, it's a little confusing. I totally understand. But anyway, so the relationship between frequency and wavelength, right? Very large, very small wavelengths. Large, small, and the wavelength ends. Frequency, though, is different. How many of these wave crests are you going to hit? Can you get hit by per second? Not very many, right? This number is going to be low. The frequency is going to be low. Frequency is going to be high, though, for these tiny wave crests, because because you're going to get hit with a ton of these per second. There's more jammed into the same amount of space. The frequency is going to be high. So because that frequency is high, this means it's going to be high energy. Energy is transmitted, when you get hit consecutively by so many crests. And the more crests per second you get hit by, the more energy is being imparted on you, right? So this is higher energies. This is lower energies. Gamma rays, the highest energy you can have, has the shortest wavelength, right? But the smallest, sorry, did I say that right? So the highest frequency, right? Did I say that wrong? The highest frequency, but the smallest wavelength, right? The distance between crests, the wavelengths can be tiny. Over here, radio waves, the largest wavelength you could have. But it's the smallest frequency. You're not going to get hit by this many waves. It's not going to be that frequent. And it's going to be the lowest energy because of that. So frequency is definitely tied to energy. Think of it that way. It's pretty obvious. Higher frequency, higher energy. Lower frequency, lower energy. You just kind of know the relationship between the wavelength and the frequency, because they're opposite each other, essentially. Okay, so we have radio waves, as we talked about. We have microwaves. Then we have infrared light, visible light, ultraviolet light, X-rays, gamma rays. We have, by the way, X-rays is sort of divvied up into soft, which are lower energy X-rays, and then hard, which are higher energy X-rays. So these are measured usually in nanometers, the wavelengths, nanometers. But you can also express them in hertz as well, and here's a hertz version. So it's like visible light, it's about 10 to the 15th hertz or so. But it's very tiny when it talks about meters, so it's going to be in the hundreds of nanometers. Okay, so this is all well and good. You can kind of see the comparison here with sizes we're talking about. Visible light is very tiny, right? Infrared is going to be to the more red. So is the microwave, and so is the radio. And then here, the visible, you have ultraviolet, X-rays, and gamma rays in that order. Just kind of know this order. Know which higher frequency than the other. Kind of quiz yourself. What's higher energy? Infrared light, or is it ultraviolet light? Higher energy is going to be ultraviolet light. Okay, so this light's all coming from space, right? Which is well and good, from all different kinds of objects and sources, including the sun. But not all of it makes it to the surface of the Earth, because our atmosphere is filled with molecules and atoms, and it blocks a lot of stuff. So with only visible radio waves and some near infrared light, near to the visual spectrum, like this part of the infrared light, makes it through the atmosphere to the ground. Everything else is blocked. If you had a telescope, you just wouldn't get any photons from a telescope that looks in the ultraviolet or the X-rays or gamma rays or some of the lower frequency radio waves. So you need to get above the atmosphere to see those things. It's called atmospheric opacity. And this is a really good, very important thing to know. It's not complicated, but it's just a kind of very basic fact that will become very important through the course. Okay. What is the wave speed of all electromagnetic waves in a vacuum? It's the speed of light, right? They're all traveling the same speed through space at the same speed. Now, light can travel through other stuff too. It can travel through water. It can travel through ice. It can travel through some wavelengths. Could actually go right through matter, without really being interfered with too much. But those travel through different mediums at different speeds. They all travel through speed of light, or travel through empty space at the same speed as the speed of light. Don't worry about memorizing these numbers too much. Just kind of know the idea of the speed of light and that it's constant at all wavelengths through empty space. It's not true through materials because it will refract. interact with molecules, and that's wavelength dependent. It depends on the wavelength of light, and it interacts with atoms. Through empty space, everything goes the same speed. The radio in your car, radio waves are getting in your car go at the same speed as gamma ray lights coming from like a stellar explosion. Okay, so there's a visible spectrum, as we know and love it, in kind of in the diagram we talked about. Okay, so what causes electromagnetic waves? Well, one of the things that can cause electromagnetic waves are accelerating charged particles. So if you move like a positron or an electron, anything that's, or a proton around, that will create an electromagnetic wave. You're disturbing the electromagnetic field through empty space, and it will cause a periodic disturbance you can will come across as a wave. Okay, so what happens when things glow? Right, we talked about things emitting radiation, and sure enough, they emit radiation, but looking for us, it happens in a very specific way. So we have this thing called a black body spectrum, and it's kind of this ideal, literally just a physical fantasy of having an object that doesn't reflect any light, and the only thing it does is glow with the temperature it's at. So like literally taking a big potato like out of the microwave and sticking it in the dark and measuring the light coming out of it, right? It's in the dark, so no light is reflecting off of it, but it's emitting all this light, right, in the infrared. It's glowing. So why do we want to study something so weird like that? Because it turns out objects that are heated up obey the black body rule pretty well, and stars essentially are giant baked potatoes cooling off in space. As I kind of mentioned in the last lecture, we're not seeing the light generated from the core of the star. Those are all gamma rays, and those are absorbed by the gases in the stellar interior. What we're seeing is the hot glow from that light and that energy being absorbed and then re-radiated out as a black body. So stars are essentially baked potatoes coming out of the microwave. The microwave analogy, the microwave is like nuclear fusion, right? It's what's heating up the center of the potato. That's what's heating up the center of the sun. But we don't see that. We see the glow from the stellar surface. Even though it's not solid, it's still gas. There's a lot of gas there, and it radiates like a black body, like a potato. So it has this beautiful curve. This is a theoretical curve generated from an equation. This is how bright the light is compared to what wavelength or what frequency you're looking at. And objects do not emit the same amount of light through at every wavelength. They emit different wavelengths of light depending at different intensities, depending on what temperature they're at. Does that make sense? So look at this curve. It has a peak here. And that peak means like what's the most light being emanated by an object at what wavelength or what frequency is that going to be at? As it turns out, that depends on its temperature. So you can tell the temperature of something just by measuring on the x-axis here what frequency this hump is at. Not the intensity, but that's kind of arbitrary. But it's the wavelength or frequency that this little arrow is at, the x-axis here. That will tell you. You can measure that. We can, right? We measure things in the sky like that. We measure how bright something is at a certain wavelength. That will tell you what temperature it's at. And then things deviate from this because it's a real life thing, and there are gases and molecules and things like that are absorbing and emitting light. And so we have like modified versions of this over the curve. So a real stellar spectrum might look something like this. Okay, so here's what I was just talking about. Where the light is sort of the curve for the light, the total output of the light is changing, right? So this is a 300K object, a 1000K object, a 4000K object, and a 7000K object. Now look what's happening. The curve's getting bigger, right? In other words, the total amount of energy, the area under the curve, is definitely getting bigger for different temperatures, right? It kind of makes sense, right? It definitely tells us that the hotter the star, the more light it's going to put out. That kind of makes sense. But also the kind of light is changing that it's putting out. Hotter stars have their peak wavelengths at higher frequencies, right? That makes sense? So our sun is here. I'll put lots of light in our visible spectrum here so we can see it. It's actually more like here, in between these two curves. But something like a potato or some other kind of object or like a planet that's not reflecting any light from the sun is going to glow like this. Totally invisible. You would need like night vision infrared goggles to even see it because all of its radiation, especially the peak radiation, is in the infrared. It's on the red side here. It's peak wavelength. So if you can calculate the peak wavelength, figure this out, you can figure out and work your way backwards to this temperature. Okay, Wien's law, and that's what Wien's law does. Wien's law states that the hotter stars produce much more high frequency light. Hotter stars, again, this is frequency here on the x-axis, getting more and more light that's on the higher frequency or the bluer side, right? It's on the bluer side. Even though it's not blue, it's just on the bluer side. It's going in that direction. Okay, so here are, so that's some radiation laws you should know that we all learned about, like Kirchhoff's laws. Right, the total energy akin to, it's not really Kirchhoff's laws, but this is radiation laws. Total energy akin to brightness is emitted proportional to the fourth power of temperature. So this says like, how big is this curve? Well, we can figure how big it is by just taking temperature to the fourth power. So this is much, sorry to zoom in here a little bit. This 60,000 Kelvin object, super hot, right? Look at the intensity and the scale of this, 10 to the 9th or whatever units this is. Super hot, it's very high and it's really shifted toward the blue here. But as you get cooler objects, look at that, 60 Kelvin. The entire radiation curve is over here. The peak of the radiation is like in the infrared. You can't even see it. It's not even anywhere near this visible part of the spectrum. And so we can calculate the total energy by just taking temperature to the fourth power. So for instance, so here's the thing in equation form. This will be on the equation sheet. So if you had an object that was twice as hot as another object, how much more energy is it putting out? Again, its temperature is doubled. It doesn't mean its total energy is doubled, right? It's two different things. Temperature doubled. How much more total energy is it putting out? All wavelengths. Temperature to the fourth. So this is 2 to the fourth. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So 16 times. You only have to double the temperature to get 16 times the amount of energy. Whether it's energy per unit area or just total energy in general, it doesn't matter. That's going to be the case. Does that make sense? And that's kind of the reason I want you to have a calculator. So maybe to do these things that, maybe too nervous to take numbers to the fourth power. Not that it's hard, but, sometimes it's just nice to have a little calculator power to fall back on when you're thinking about these things. Okay, so here's Wien's law, what we talked about, right? The wavelength of light is inversely proportional to the temperature. The wavelength is the wavelength max, is the maximum, the peak wavelength here. It's not all wavelengths. So again, you increase the temperature, this denominator gets bigger, this fraction gets smaller, so the peak wavelength is going to be at smaller wavelengths. Wavelength is inversely proportional, of course, to frequency. And you can kind of see in the x-axis down here for all these, how they change. So temperature goes up, right? Wavelength, the peak wavelength here goes down, right? Smaller wavelength, but the frequency goes higher. Does that make sense? That's another one where the relationship between wavelength and frequency comes in handy when trying to figure that out. But this is usually done in wavelengths. We're talking about Wien's law. Now, if I were to talk about frequency, I would say frequency is directly proportional to the temperature, right? Temperature goes up, frequency goes up. Does that make sense? Don't worry too much about that. I'm not going to ask you super complicated questions about this. I mean, maybe this would be it. Something like this. It's the relationships here. So maybe one good thing to kind of memorize is maybe, I mean, this will be on the equation sheet, just so you know, but know like how things are going to change. Like know how frequency changes and how the wavelength changes when the frequency changes. Know that relationship. That will probably serve you pretty well. Okay, Doppler shift. Things coming toward you get blue shifted. In other words, all of the spectrum stuff, including that whole spectral distribution, right? That hump gets pushed to the blue end, to higher frequencies when it's going toward you. If something's moving away from you, the frequency gets lower, the wavelength gets longer, and that's called redshift. So blue shift coming towards you, 3D. Blue shift coming toward you, red shift coming away from you. Okay, let's do chapter 4. Any questions about chapter 3 or radiation in general? Just a couple confusing things there, but I think you'll be able to get it. You just shoot your questions, I'll keep an eye out on chat. Okay, that's a missing S there. Spectroscopy is the study of interaction of matter and light. Okay, spectroscopy is not the study of rainbows. It is not the study of how bright a light is. It is the study of how matter interacts with light, how atoms and molecules, but atoms at a fundamental point, are interacting with light. And then a spectroscope is like is a device used to kind of do that. It's kind of similar to that diffraction grating you put up to your eye during a demonstration we had in class, right? It's kind of a spectroscope. Instead of your eye, it could be like a CCD back there, just taking a picture of that. So you can take a look at it later. It used to be a camera, like literally a film camera. Okay, so prisms, we don't use prisms to do this anymore, really. We use diffraction gratings, just like we had in class. We take light, we put it through a slit just to get a little part of the light out so things are nice and clean. The glass bends the light at different frequencies, different ways, and then it spreads out onto a rainbow. So we have a beautiful rainbow here, a continuous source. Okay, so we have a couple different deals going on here. We have emission lines and we have absorption lines, right? We can generate, we also have a continuous source. So we have a hot light bulb, put it through a prism or a diffraction grating, you get a beautiful rainbow. It produces colors evenly, or maybe not evenly, but for our eyes, at least from this rainbow point of view, it seems to be evenly. We get a nice, beautiful rainbow. But if we take a gas and we heat it up, or we send electricity through it like we did in class, it goes through a diffraction grating, and it makes these very specific lines that are specific to the gas, because those atoms will absorb light at very specific wavelengths. We don't get a rainbow, we get very specific lines. Does that make sense? And then absorption spectrum is similar. We take a nice cool gas and we send a continuous spectrum through it, and it will absorb light. It will create black lines in this continuous spectrum at the exact same wavelengths as these. Okay, Kirchhoff, everyone's Favorite German physicists? There's so many good German physicists. I don't know if Kirchhoff is my favorite. I'm an astronomer. He might be my favorite physicist, German physicist. But anyway, he's definitely up there. Luminous, solid, liquid, or dense gas produces a continuous spectrum, just like I said. Kind of summarizes what I just kind of talked about. And then here's that sort of triple diagram. It kind of combines all three ideas into one, maybe somewhat slightly more confusing diagram. But I think you get the idea. Right? In this one, you're just taking the energized gas and not looking at this reflected source. So that's why it's coming out like at a 90-degree angle here. And taking the energized gas, and so you get the emission spectrum that way. Okay, so we can, with emission spectrum and absorption spectrum, we can use it to identify elements. They're like fingerprints, different elements: hydrogen, sodium, helium, neon, and mercury, all of which we observed in class. Remember neon? Remember how many branches of different lines of color there were when we turned on neon? It's like a forest. Okay, so there's the absorption spectrum. I won't go over that because I just kind of talked about that. Why is there a barcode here? Oh, I see. I thought that was some weird clipping I did. So barcodes are kind of like, it could be read like a barcode. Absorption spectrums. Literally, like, it's very specific because it comes out a number, it comes out to be a code. This comes out to be a code of what elements this cold gas is made out of. What's causing those things? Electrons, right? Electrons are moving up and down and causing those things, that light to be absorbed or transmitted at specific frequencies. So again, we have atoms, right? We have protons and or neutrons at the center of the atom, the nucleus, and we have electrons that go around it. Very fast, essentially the speed of light. So those things, they're going around very fast, and as they absorb energy, they go to higher energy states, right? And as they lose energy, they can go down back to those lower energy states and emit that light as a photon. So it absorbs the light at a specific wavelength, it emits the light at a certain wavelength. The electrons are what move up and down in energy states, and that's what changes. That changes per element because the amount of electrons is determined within a varying degree, determined by the amount of protons in the nucleus. So at different elements, you have different number of protons, you can support a different number and different configuration of electrons. So that's how that's why different elements produce different spectrum, because they have different electrons going around them, different amounts in different configurations. Oh, and there's what I was just talking about. I sort of got ahead of myself. Okay, so let's skip over that. So here we have a beautiful glowing cloud of gas in space. This is a real glowing cloud. So what we do is we're getting this light from this cloud, but we want to measure a whole spectrum, right? So we want to take a look at the infrared light and all the way to the blue light. So this is just a part of the spectrum, like the visual part of the spectrum. So when we measure all that, we don't see a continuous spectrum. We see very specific wavelengths. And what we do is we take the brightness of each of these wavelengths and we assign it some value. Okay, this is super bright. We'll make this a 5. This is kind of dim. This light is dimmer because they're not all the same brightness. This is dimmer. I'll call that a 2. Put this on the plot here. So pretty soon we have a plot of brightness for all the different wavelengths. And that gives us what's called a spectrum. And that spectrum will tell us exactly what elements this glowing cloud of gas is made out of. Now, as we're going to learn in this chapter, this is not just emission lines, glowing clouds of gas, but there's also stuff absorbing light as well from nearby stars, for instance, that are producing more of a continuous spectrum. And so these are absorption features as well. Okay, so we don't have just atoms. Sometimes atoms combine to create molecules. Those molecules, of course, have electrons, just like atoms do, and they can absorb light, and they can emit light. But they do that at even more complicated frequencies. And not only because of that, because they have a lot of electrons and they're sharing electrons and things like that, but they're also doing other things. Like two molecules like carbon monoxide here, CO, these molecules are vibrating back and forth, literally like this, these two atoms. And as they do that, they can absorb and emit energies at other wavelengths. So not only do you have electrons being absorbed, controlling what's going on as far as the atomic point of view, but from the molecular point of view, you have all this spring action going on, which affects how an atom absorbs light, and also rotating. As these things rotate, because it's a space, right? Things are vibrating and rotating and going all kinds of crazy things as they're being energized. And as they do that, they emit light at all different kinds of frequencies. So as a result, molecular spectrum are very much more complicated and numerous, and many more numerous lines than the atomic version. So this are two simple, really simple elements. These are the most two abundant objects in the universe, or elements, I should say. Hydrogen, H, atomic, not bound to any other atom. And then we also have hydrogen gas, H2, molecular hydrogen, bound together, two hydrogen atoms bound together into a molecule. You can see how terribly different they are from each other just by being connected to atoms. Alrighty, so we have line broadening, can be due to a varying amount of causes. So spectral lines aren't just like go up and go down at certain wavelengths. I mean, if you look at it from a very narrow point of view, it does look like that. And kind of your homework kind of gives you that impression, but in reality, it's actually not that case. Even mathematically, it's not that case. We have to get into a little more sophisticated mathematics to see this. The lines are broad, so these emission lines or absorption lines go like this. They start at some frequency lower than what you would expect and go up. They get really intense here at where you would expect the single line to be, and then they get lower intensity here. Why is that? Well, quantum mechanics is one answer. Not all the atoms are moving at the same speed, at the same temperature. Just from a thermodynamic point of view, they're going to do that. But also, there are other things that are going on as well. I think that's in it. Oh. So there's different ways that we can broaden lines. We can do that from motion. I'm missing a slide, I think, here. Anyway, maybe we want to write this down. So we have motion. We have rotation. Rotating stars, for instance, can produce red shifts and blue shifts in the same imperceptible dot of light we see. So we see red shifts and blue shifts on top of each other. That has the effect of broadening out absorption features or emission features. And then being under pressure can broaden the lines. Magnetic fields that these gases are present under can also split the lines and cause them to broaden as well. So yeah, those are kind of some of the highlights of what can broaden a line. Hopefully that helps. And you don't need any more detail than that. I mean, in your book there are some diagrams kind of give you an idea about this, but let's kind of know in general the types of things that can broaden lines. So what can we gain from spectral lines? What does all this mean? What do we care? Just by looking at a telescope at light, never even going to a distant star or planet, we can tell its chemical composition, what it's made out of, what its temperature is, whether it has a strong magnetic field. We can figure out if it's moving toward or away from us or how much it's rotating. We can tell how much pressure a gas is under. And then we can use all that information to construct a physical model. And all of a sudden we have like models for how these things work, and we know the density of something, and we know what the temperature is and the pressure at the center of the sun, and everything else comes out of that. It's pretty amazing. Light is incredible. Okay, let's talk about telescopes, our final chapter. We have a lens. It's kind of the most basic thing of manipulating light. We take light through a lens, it bends the light, and we can actually create a lens where light is bent at the edges a lot, and then we have a piece of glass here that doesn't bend it a whole lot. Then we have just a straight piece of glass that doesn't bend the light at all. And if we reverse out on the other side, it bends the light so that all the light that's coming in from the other side is focused, right? It comes to a focus point where you can actually look and maybe see a magnified or a brighter view of everything this sees in a very small area. So we can form images two ways. We can form images that way with a lens. That's called refraction. Or we can use a mirror to bounce light and essentially kind of do the same thing. That's called reflection. Those kind of telescopes are called reflectors. So light comes here, and if it's not high enough energy, it doesn't go through it, it bounces off, and then it bounces the light here. But we're going to shape this mirror so that this light, when it bounces off, comes off at a different angle. It's going to also focus here, and so on, until this light going right through the center just bounces straight back. And then all of a sudden we have the same deal we have with a lens, is that it's all focused here at the focal point, and we have another magnified image. And not only magnified, but brighter, right? You're having a lot of brightness of it could be a very small area of the sky in a very small area as well at the focal point. Okay, so here are like sort of what reflectors and refractors do. Using light to bend, using a lens, just like we saw at Cincinnati Observatory for refractors, and then reflectors uses the lens, there's a mirror, I should say, to bounce the light. This particular reflector, called the Newtonian reflector, just bounces light out of the tube, out of the side of the tube here, but it has the same idea, right? It uses a mirror to reflect the light to a focal point, which is like about here. And then there's like an eyepiece in both of these cases, where the light can be further magnified. Or not magnified, I could do the reverse, depending on what you want to look at. All modern telescopes are reflectors. Why is that? They're easier to build. Lenses can mess up an image. And because light will travel through a lens differently at different wavelengths, so you gotta like compensate for all that because you want all the wavelengths to be at the same focus point, so you have to do a lot of tricks to get that to work. So refractors are bad in that sense. Lenses also absorb light, so it's bad. Large lenses can be very heavy, as we saw from the Cincinnati Observatory. That thing weighed like, what, 1,000 pounds at least, I think Dean told us. And then also a lens needs two nice, beautifully curved and polished optical surfaces, right? The front and the back of the lens. The mirror, you just need one surface of the mirror to be perfect, and you're good to go. So resolving power. We have defined this thing called resolution, which is kind of very akin to the resolution on your television, but we're taking a look at things in the sky and how detailed you can get things. So we're talking about pixels, right? The more pixels per square inch that you have is good, right? 4K, the amount of pixels you have on your screen for that is much better than like regular HD, right? Why is that? Because the pixels are smaller, right? You have smaller pixels and you're jamming them into a much smaller area. Very similar to when we talk about resolutions of things when we look at it through a telescope. How tiny are the best objects we can see? What limits our resolution? You would think it would be infinite, right? Theoretically, it's not. Even theoretically, there's a limit, and that's diffraction. Diffraction is a real physical effect. It is dependent on the size of your telescope. So through bigger telescopes, you can get something that looks like this versus what looks like this. And what's happening there, you have better resolution, smaller resolution, the smallest tiny bit you can resolve, i.e. a pixel. The pixels are smaller. So that tells you, kind of gives you an idea for how that works, right? Smaller resolution is better. Atmospheric blurring. So that light coming through the atmosphere is like being in the bottom of a swimming pool, looking up at the top, and everything starts getting wavery. So literally the star is bouncing around your view, and that's because the atmosphere is acting like a lens that is moving it around, like almost teasing you. So better seeing means that it's just not bouncing around as much. Seeing is all about the Earth's atmosphere. So you go above Earth's atmosphere, you don't ever have to worry about seeing. But astronomers are always struggling with seeing. So adaptive optics control mirrors based on temperature and orientation. So that's the other kind of funky thing that the real world teaches us. So if you have a mirror that's at a certain temperature, and then it cools down maybe as the night goes along, and the night gets colder, your thing is going to change. Your shape of the mirror is going to change, believe it or not, as it expands and contracts, right? The shape of the mirror. So it has a real effect. So you need adaptive optics to kind of correct for that expansion. We try to minimize that in telescope design by, with the types of materials we produce and the way we cool down the telescope before we observe. And also the orientation will affect that as well. So that's active optics. Adaptive optics actually tracks the atmospheric changes in the atmosphere and adjusts in real time. What we do is we shoot a laser up. It's usually like sodium laser, and it actually hits a layer of, sorry, it's not a sodium laser, but it hits a layer of gas molecules in the atmosphere that glows at that specific wavelengths. So we kind of use that to our advantage to hit the atmosphere in a certain way and cause it to glow. And we create like a sort of an artificial star that's going through the atmosphere. We look at that with a telescope. We see how that messed up that little dot is as the atmosphere is blurring. And in real time, kind of like a Snapchat filter, it compensates the telescope optics in real time for whatever the atmosphere is doing. It's pretty amazing, and it works very well. You can essentially make images here on Earth that look like the Hubble Space Telescope. Okay, radio telescopes. We're almost done. Radio telescopes. They're similar to optical reflecting telescopes. In other words, light just comes down here, reflects off the radio dish to a receiver right here. Oh, I'm using my thing again. Sorry. So used to doing this in class. So it comes off, the light comes down, hits the dish into that receiver that's on the arm there. And that's where all the electronics are that gets the signal. So it's a prime focus telescope. That means it's not like a Newtonian or any kind of a telescope where you shoot things out the side. It's literally just focused to that point on the arm. And again, this is in West Virginia. This is not very far, terribly far from Cincinnati. If you ever want to do a fun day trip to the beautiful mountains of West Virginia. And then also, because radio telescopes are so big, first of all, what are we looking at? Radio waves, right? Really long wavelengths. So because of that, they'll bounce off of materials and they'll act the way we want them to, even with very imperfected surfaces. Surfaces that are even wavy, on like a scale of maybe your hand or something like that. And you want it to be as good as possible. Because the wavelengths are so long, there's a lot of tolerance for that. So you can make really big, essentially wire mesh dishes that reflect radio waves very well because the longer wavelengths are just not affected by tiny imperfections. I guess that was what I was trying to say in a long roundabout way. Here's a good example of what happens. I forgot I had this slide. Incoming radiation, it goes to the focus. So what are the interesting things about radio astronomy? Again, radio is not sound. Radio waves are light. Your car is a telescope. It is a light telescope. It is, getting in light from your favorite radio station and translating those that light into sound. So anyway, the longer wavelengths of radio waves means very poor angular resolution. So do you remember that? I don't have it here, but that formula, right? It's that we kind of went over in class a lot. It is the wavelength of light over the diameter of the telescope. That is the resolution, right? You want small resolution. So the bigger telescope you have, the better resolution you're going to have. What's better? Smaller. Smaller resolution is better, right? How many pixels can you pack into your television per square inch? That will give you a better picture. Same thing here. The angular resolution, the resolution that you're trying to get is as small as possible. So if it's wavelength over telescope diameter, if that's the fraction we're talking about, big wavelength, big resolution. That's bad, right? So you got to make this telescope big. Luckily, you can make them big, and it will work really well. So big telescope means that denominator is going to get big, right? And the angular resolution is going to get smaller. So it kind of compensates for that. So longer wavelength means poor angular resolution, in other words, bigger. Radio waves have less energy than higher frequency light and need large dishes to counter both. So that's right, you have less energy, you need more gathering surface area to get as many photons as you can to get the image you want. Photons, we want to get as many photons as we can. We talk about it all the time, literally like that. We call telescopes photon buckets. Believe it or not, that is like a real thing astronomers joke about. Or light buckets. Okay, so also in radio, we can observe 24 hours a day. We can observe in clouds and rain and snow. They don't interfere. The radio waves go right through all that stuff. The radio waves we do get through the atmosphere, that window, it's a relatively small window that the atmosphere does let through. And we can get totally different information from different wavelengths. And this is a general statement, depending on what wavelengths we're looking at. So we want to get different wavelengths of light because it tells us a lot of what's going on. So here's the ALMA array. Many dishes set on a mobile array. So we're able to move these around, as we talked about in class, to different configurations to get different resolution on the parts of the image that we want. So it's kind of complicated. There's a lot of math involved. And this is an interferometer. Interferometer is like combining the signal from many smaller telescopes to make it the equivalent of one giant telescope that would be this large. And then you get higher resolution in certain areas, depending on how these are bundled. These are all mobile, just like the Very Large Array. Okay, so I think that covers everything that we're going to cover for the exam. Do you guys have any questions? Again, Thursday, same regular class time, 9:30. Just keep in mind all the stuff I told you, and you should be just fine. Don't be nervous. I think you guys are going to do great. Alrighty, thanks for coming, and have a good weekend. I'll see you on Tuesday. Thanks, Tony. Thanks, Lou.